In this theorem, we need to prove that the probability of simultaneous happening of two events A and B is given by P A intersection B equals to PA into P B oblique A, where P of A should not be equal to 0. Okay. So what essentially it is the multiplication theorem, okay, multiplication theorem of probability. Now P B oblique A stands for essentially probability of happening of B when A has already happened. This is the conditional probability. Conditional probability. This is probability of B B condition to A. Okay. Similarly, probability A oblique B would be probability of A condition to B. Okay, so let's try and prove that. Your sample space, let us assume it to be N. Okay, and A and B are events associated with same sample space, okay. Then in that case your sample space S of random experiment with exhaustive number of outcomes is N. Okay. Now by definition, what would be probability of A intersection B? It will essentially be number of outcomes associated with A intersection B upon number of total outcomes, right? So that would be as written here, right? N A intersection B upon N S. Now, for the conditional probability, now A oblique B, that means happening of A under the condition that B has happened already, the favorable outcomes must be out of the same points of B. Okay, so your sample space becomes B. So P A oblique B would essentially be N A intersection B upon N B. Okay, because the sample space would be B, and similarly P B oblique A, probability of B condition to A would be N A intersection B or B intersection A upon N A. Okay. Now let's look at what would our PA intersection B would be. That would equal to N from here, rewriting this would equal to NA upon NS into NA intersection B upon NA. What have we done? We have just multiplied it and divided by NA. Multiplied and divided by NA. Okay, so this would give us probability of A into the conditional probability condition to A. So conditional probability of B condition to A. And similarly, P A intersection B can also be NB upon NS into NA intersection B upon NB, that would equal to probability B into probability condition to B. Okay, what essentially are we trying to say in this theorem is that the simultaneous happening of two events, is actually it's actually the product of two probabilities, which is essentially the probability of the first event that happens and the probability of the second event happening when first event has already happened. So this is essentially probability of the first event happening and multiplied by probability of the second event happening when first event has already happened. Okay, so in this case, B is happening first. In this case, A is happening first.